Hello.
Hello.
Hi, Arif.
Yeah, now I can see you. How are you?
I'm good. I guess it's very sunny over here right now.
Yeah, it's very cloudy in London, as always.
Yeah. So we're starting in 4 minutes, right?
Yes.
And you're going to, is the Q&A going to work? So you're going to just read the questions to me or like, moderate more broadly?
So there will be people joining on Zoom and there will be people joining on the campus as well.
Mm-hmm.
So I will ask everyone to type their questions in the chat, and maybe when the Q&A session comes, if people are fine with it, they can ask by themselves if they want.
But somebody's going to moderate and decide who has the floor and that sort of thing.
That is me.
That is you. Okay, good. No, just because I'm not going. So what I will do, I assume, is not look at the questions in the chat.
Mm-hmm.
Or, as I go through, I'll just do my 35 to 40 minutes and then you'll moderate the questions. Okay. And should we check that I can share my screen?
Yes, please. Yes, please. I think we've enabled.
I should be enabled. Okay. Let me try it out. Can you see this?
Yes. By the way, I think there are still people coming in the room. Would it be okay if we can start in, let's say, 4:20 in 7 minutes?
Sure, we can do that, but we still keep it the same duration, right?
Yeah, sure.
Let me just check this. I can try to finish sooner so it works. Okay, fine. Mm-hmm. That's fine. So what shall I just wait here?
Yeah, if it's fine. By the way, we are recording our events usually. Are you okay with recordings? And we will also
I guess I don't know. Usually people ask this ahead of time. What I can say now is that I'm okay with you recording it, but not making it public until the event is over. And then depending on how it goes, I'm happy. But I think I'm not. I don't know what these things are like. Is everyone agreeing to have it recorded and posted?
Yeah, usually, yeah.
Usually.
Yeah. For now, I think we've gone over I don't know, 10 speakers, and all of them were okay.
Okay, fine. And then, so what will you do with the recording?
We're gonna publish with our members only.
Okay, with your members. Okay, fine. Yeah, sure.
Yeah.
Yeah, I mean, let's record it, and then if something terrible comes up, then I'll reserve the right to say, let's not like keep it for posterity, but it's never happened in previous talks that I've done, and I've done a lot of them. So
by the way, we can publish it with you at first, and then if you say you're fine with it, then
sure, sounds good. Yeah, again, I assume it'll be fine. So, but yeah, it's good to have the option.
But by the way, should I refer you as Professor Diaz Enodon, or do you have?
So when you first introduced me, I think yes, and then I don't know what you're doing with the others, but first, again, I'm very aware of the fact, and I've seen this for a long time. You are in meetings, and the men are referred to as Professor whatever, and people just call me Laura. So, and this happens to other women. So I'm, because I also look relatively young, I'm told. So I think at the beginning it makes sense to use my title, but then of course, if you're being consistent with how you're treating all the speakers, then fine. But I think at the beginning you should use the title. Yeah, just consistency is important. What I have noticed in many fora is that you have a particular treatment for some people and a different treatment for other people, including me. So let me actually close the curtain because it's too bright.
Okay. Mm-hmm.
I don't know what you're doing with others, Arif. Are you?
Hmm?
Is that what you've been doing?
No,
The-
usually I introduce them as professor. Yeah.
Okay. Yeah.
I think all the time, not usually. All the time I've did this. Yeah.
Yeah, I think consistency again. My students I get them to call me Laura, but I've seen that in public events this has happened many times.
By the way, I also asked this question because I couldn't decide if I should say Professor Anadon or Professor Diaz Anadon.
People do both. You can say that you are good at actually pronouncing it. So Diaz Anadon works. Yeah. It's Diaz in Spanish, of course, but Diaz is some people get tripped, but you don't. So that I'm not very fussy about.
Okay.
So this is the last day of your event?
Yes, we have one more panel after this, and we'll be over. Yeah.
And then you can take a break.
Yeah, it was a bit long journey.
Yeah. No, events, whenever you do events, it always takes much more than you think. And then, you leave it a few months, you kind of forget about it, you commit to doing another one and organizing another one, and then it's all over again.
Yeah. But I think it's important, like the important thing is that when you feel proud of yourself at the end, right?
Yeah. Yes.
Literally.
But I do forget always whenever I organize anything, how much time and mental bandwidth it takes. So
yeah. You always forget the negative aspects of the organization.
Yeah, it's like having children. You forget after a year or two, you forget how much work it was, and then you probably haven't had that experience. But
okay, right now I think our audience is joining in the room. Yeah, and if everything is fine with the live audience as well, we can start in a minute.
Shall I share my screen, Arif?
Sure. Yeah.
Yep.
Thank you everyone for coming. Today we have Professor Laura Diaz Anadon with us. Professor Laura Diaz Anadon holds the chaired professorship of climate change policy at the University of Cambridge. At Cambridge, she is also the director of Cambridge Center for Environment and Energy and Natural Resource Governance, and fellow elect at St. John's College. She is also a long-standing research associate at the Belfer Center for Science and International Affairs at the Harvard Kennedy School at Harvard University, where she's a visiting scholar for 2021 and 2022. Without further ado, I want to leave the microphone to Professor Diaz Anadon.
Thank you very much, Ari, for the kind introduction and for the invitation to join your symposium. I understand you've been very busy for a few days. Over the next 35 to 40 minutes, I'll try to cover a topic that is very big, which is on designing policy to accelerate innovation towards net zero. I will necessarily not cover everything, but I'm hoping to give you a sense of what the policy debates are right now and where some of my research and the research of some other groups around the world have been going. I think over the past 10 years or so, we've learned a lot about what works, what doesn't work, or how to make things work better. And I'm going to be presenting the work that I've done with a range of co-authors that I will show you at the very end. So why am I talking to you today about innovation towards net zero in the energy sector? First of all, this is something that many of you or most of you will know. We've just come out of the COP26, which is one of the international meetings that have been happening every year for 26 years. Last year it didn't happen because of COVID, to address our greenhouse gas emissions. And what we have known now for a while is that the current greenhouse gas emissions trajectories and those of CO2 more specifically are not consistent with the goals of the Paris Agreement. I've shown here on the right a graph that shows in black historical emissions and then different trajectories going over to 2100. If we just focus on going over to 2050, what we see is that fortunately, the worst case scenarios, given the policies that have been put in place and the pledges that have been made as part of the nationally determined contributions, which is this mechanism that was created in the Paris Agreement, luckily we're avoiding these gray trajectories, 5 degrees, 4 degrees. Just before the Paris Agreement, we were on track for around 3.7 degrees Celsius of warming. Right now, we are already 1.1 degrees Celsius over pre-industrial global average temperatures. And it is true that since around 1997, when the Kyoto Protocol was signed, the global carbon intensity, which is the CO2 emissions carbon intensity per unit of GDP, has been declining at about 1% per year. So this is, good to some extent, but of course, as this graph makes clear, to meet the 1.5 degrees Paris aspirational goal, which was a goal that was reinforced in many declarations in the Glasgow Pact, we would need to increase the rate of decarbonization, the rate of decrease of carbon intensity by over 1 order of magnitude. And again, even after the Glasgow Pact, this is one graph, a slightly more updated graph produced by the UNFCCC, the United Nations Framework Convention on Climate Change. Again, when you look at up to 2030, which is the date by which the Intergovernmental Panel on Climate Change, of which I'm one of the lead authors of, has indicated we need to more or less halve emissions, we're not there, right? So the naturally determined contributions are not consistent with this. So we're not doing enough, and I'm going to be focusing on the role of technology innovation and more specifically the role of policy and technology innovation. But first, it's really important to define what I mean by technology innovation. There are lots of different definitions. When we think about it from the perspective of climate change mitigation, most of us and many literatures focus on an expansive definition that includes from research on the left-hand side of this graph to diffusion, to having an impact on the market, on how we live, on the emissions on the ground. And the important thing about this graph, beyond the fact that it's not just research, that it's not just scientists in the lab, we have these linkages between the different processes, between diffusion and research, between demonstration and development. And that's a very important thing, as I will mention. The other thing that I wanted to show in this graph is that a wide range of policies shape, we know from not just energy, but other sectors, shape the pace and direction of technological innovation. So again, this is a stylized graph. There are a lot of different ways of putting this. A useful distinction for policy purposes is this technology push versus market pull policy. So technology push here on the left, things like public research and development funding, tax credits, education, and on the right-hand side, things like demand pull policies, creating early markets, pricing carbon, and things like this. And the last thing I wanted to mention about this slide is that there are different, because the innovation process includes a wide range of stages and of course a wide range of actors. You can clearly see here that you have actors that go from finance to scientists to civil society to users that are involved with diffusion and provide feedback. The other thing is that there are different indicators. So on the bottom yellow bar, we have different indicators that are proxies for different stages of the innovation process. None of them are perfect. They all have limitations, but we do have a sense of what's happening at different stages, and the data is, has different levels of quality in different stages. So why? Okay, we've talked about innovation. What do we know? Well, net zero emissions, which is the goal that about 130 countries have announced to stabilize emissions, because of course, to actually stabilize the global average temperature, any temperature, 1.5 at 2 degrees, we have to, at some point, stop emitting greenhouse gas emissions, right? So starting from that, even if we wanted to stabilize at 4 degrees, we would have to stop at some point, right? But around 130 countries have announced or are considering targets to get to net zero emissions between around 2050 and 2070. The most recent pledge was made during the Glasgow conference by India to get to net zero by 2070, China by 2060, and many other countries, including the UK by 2050. And this graph on the left was produced by the International Energy Agency. It's, I'm not going to be defending specific numbers, but the key message here is that to get to net zero emissions by any of these dates, first, we have some technologies available, and I'll get to in a second the major improvement we've seen in both cost and deployment of things like solar and PV and lithium-ion batteries. So a lot of the technologies we need, we have. And again, as I will explain, thanks to a lot of the policies that have been put in place and some private sector response to these policies. But around 50%, if not more, of these emissions are not yet widespread, commercially available at a large scale. So we have in this graph the part that is in yellow and orange, demonstration, large prototypes. Most of these technologies are in the areas of either aviation, shipping, energy-intensive industries, these hard to decarbonize sectors, as well as firm power generation. So and greenhouse gas removal, which again is another topic in and of itself. I'm not going to get too much on that. But there are a lot of technologies where it's really important that we make a lot more progress, that we begin scaling up and commercializing those technologies. And of course, the technologies that we already have, we need to scale up. We need to diffuse even more quickly. So technology innovation is important because we need it to meet net zero goals. I also wanted to frame technology innovation from a different perspective in the energy sector. And I don't know how many of you are familiar with this iPad or Kai identity. It's just an identity, so very, very simple. As you can see, CO2 emissions, what you have on the left is the same as what you have on the right, and different drivers. This is just a way of understanding this. It's quite useful when you're doing back of the envelope calculations for things. And what you see is that when we think about energy innovation, most frequently what we think about is its impact on the right-hand side here, on carbon intensity, which is carbon emitted per unit energy produced. So this is what when you, for example, replace a coal power plant with a wind farm, you're affecting this term, right? So this is the way in which most people have thought about the role of technology innovation in reducing carbon emissions. But what you see, and what I will hopefully show you by the end of this presentation, and of course there's a lot of other people that are working in this space, is that energy innovation also affects this second term of the processes that are behind this second term, or this term of the Kai identity, energy intensity, the energy needed to generate or associated with 1 unit energy of GDP. And again, and this is because, of course, we have energy efficiency, innovation in energy efficiency technologies, for example. And it also affects, of course, income per capita, because as I will indicate, there are a lot of new industries, new jobs, spillover effects that also shape more broadly, income and other parts of the economy and welfare. Of course, even more indirectly, we can go back to population. But the message I'm trying to bring here is that it's not just that we need these technologies on the ground, they drive a lot of these different factors. And one way of thinking about this role of innovation is that it shapes both the costs and the benefits of mitigating climate change. So when we think about the cost of mitigating climate change, I've mentioned earlier, if we have more affordable, clean technologies, it will cost less to reduce emissions. And as I will show in many cases, and again, in the longer term, all results, including a recent Treasury review, where I was one of the advisors in the economics section, along with one of your, Lord Nick Stern, so one of your faculty members. And we see that the innovation affects the cost of mitigation, but also, of course, the transition cost. So when we think about manual workers in sectors that might become obsolete or that will lose out, so it really shapes the cost of the transition, certainly in the short to medium term. And it also shapes the benefits and the positive negative impacts. And here again, when we think about the big scope of innovation, we can think about new industries, increased competitiveness or decreased competitiveness, improved health outcomes. There's a lot of work, as many of you I'm sure know, on what are the impacts on health of reducing internal combustion engines for gasoline vehicles with electric vehicles and things like that. We also have impacts on ecosystem services, natural capital, And there was the recent Dasgupta review from, again, a colleague from Cambridge who has been working on this. Climate change damages mental health, more cohesive communities. And this is just on the right, this kind of donut-inspired graph that we produced as part of another committee in the east of England, in the Cambridgeshire and Peterborough region, looking at all of these different factors. And of course, as you can see from the Sustainable Development Goals, which more or less mirror this, or vice versa, they're shaped by the evolution of technologies, which include processes and devices. But in the last piece here of how a useful way of thinking about innovation is actually from the political economy, politics, public policy, and innovation studies literature. There's over the past 10 years, maybe a little bit less than that, there's been a huge amount of research suggesting that the value of a strategy for greenhouse gas mitigation, emphasizing the impacts, and especially positive impacts, on innovation and competitiveness. So there is a lot of research looking at public opinion, voter behavior, and this sort of research, political science, public policy, that shows that there's more support. Again, this is not very surprising, but we do have quite a solid evidence on this sort of thing, that that you have more sustainability over time, and voters and the public will support decarbonization and the fast decarbonization we need if they perceive there will be benefits in terms of competitiveness, of new jobs, industries, as well as health and other co-benefits, so biodiversity and natural capital, for example. In addition, we also have from research on, again, politics, political economy, that when you have these new players and actors that can benefit from climate change mitigation, you also create a new group of actors that can counterbalance the incumbents in the fossil energy space. Again, this is really important. There's a lot of great research on the role that the incumbents fossil fuel companies have played over the past, well, a long time actually now, decades on this topic. And it's clear that when you have another, again, interest group in a sense that is playing a role here, it's easier to overcome lock-in and get rid of some of the policy, the sticky policy. Of course, then you have another set of interests that might make it harder to pursue the even next generation of technologies that may have other benefits. So we do have these additional reasons to ratchet up ambition over time, both in terms of the support from the public as well as the support from other actors that are important in the political process. So with that in mind, hopefully I'm giving you a sense of the different kind of literatures that are looking at or increasingly engaged with innovation. It was more of an isolated area, but now is really touching on many areas. I wanted to talk about the first part, which is the cost of energy technologies. And this is one of the areas in which we've seen, positive surprises for change. When we think about the climate change area, most of the things we've seen in terms of impacts have been negative surprises. Here we have had some positive surprises. We've seen that the cost of climate change mitigation technologies, at least the ones for which we have data, there's a couple of exceptions, have come down really quickly. And here there are just some pictures, onshore wind capital costs, lithium-ion batteries, LED lighting, replacing things like incandescent light bulbs and CFLs, onshore and offshore wind. And just as a summary, over the past 10 years, and of course, the cost of many of these technologies have been coming down, by, let's say in the case of solar, 3 orders of magnitude over the past 30, 40 years. What we've seen is that the cost of PV, lithium-ion batteries, and solid-state lighting have come down by about 80 to 90% just over the past 10 years. For on and onshore wind, it's been more around 50%. And actually here in the case of the offshore wind, the UK has been one of the places where this has been most visible. And the important thing about this is that it's not, we have these cost reductions, and these cost reductions were things that were not really forecasted. So technology forecasting is, trying to understand or trying to predict what the cost of different technologies are going to be in the future is widely used in many areas. It's very widely, the forecasting the cost of future energy technologies is really relied upon in the design of climate mitigation efforts. So in energy economic models, integrated assessment models, such as those used in the IPCC, cost benefits analysis, which is required in many countries to support regulation, including the UK in many areas, and of course, firm investments. When you think about where different companies in both in the energy sector and outside, they think about, well, what is going to happen to these technologies? Should we get in or out? What should we do about this? And there are a couple of things I want to say about technology forecasting beyond saying how it hasn't really been, how there are ways to improve what we've been doing. There have been many calls over time to reflect uncertainty around the future cost of these parameters. So often when companies, analysts, researchers, policymakers do forecasting, they use a deterministic approach. So either just use one point, they're deterministic, or maybe they have a high and low estimate, do a sensitivity analysis. And again, there have been many calls, included by the Nobel Prize winner Nordhaus, as well as myself and colleagues and many other people, that we need to move to uncertainty forecasting, because as I will show you, there's a lot of uncertainty around this. Nobody can really see the future perfectly. And there have been there's been a growing effort to be probabilistic about this, to use probabilistic methods, stochastic approaches in the design of climate policies, reflecting the uncertain nature of things like the cost of technologies. Of course, other things are also uncertain, such as demand and prices. But this one, as I will show you, is quite important and has been seen one of these parameters that makes a big difference. So there have been efforts to do expert and model-based probabilistic forecasting. But to my complete surprise, a few years ago when we started on this particular project, we really didn't know whether anything was accurate, how it worked, whether or not they were good or not at actually predicting costs. There are two main types of approaches for probabilistic forecasting. Some are based on experts, and here I'm not going to go through this table, don't worry. But there are three main types, or four actually, of expert-based approaches, just kind of asking somebody and putting a number in a model in a cost-benefits analysis. This is what I'm calling and what we're calling in this paper and structured expert input. Then we have expert elicitations, which is a very cumbersome way, but trying to de-bias, to get rid of some of these biases that we all know, and maybe many of you have studied, anchoring, availability, and things like this. And then, group-based methods and prediction markets. We cover expert elicitations because they're probabilistic, they have been increasingly used, they try to get rid of biases, and they don't assume that previous trajectories continue. So there are some reasons why this might be useful. And then we also use different model-based, so data-based forecasting approaches. Some of them, the most widely used ones, are assuming that the future cost of technologies are a function of deployment, Wright's law. And then the more slow are assuming that future cost of technologies are a function of previous experience over time. And again, they're widely used in these models I'm talking about, both in cost benefits analysis, energy economic models, integrated assessment models. And here are some examples just to give you a sense of what these things look like. Here we have expert forecasts for PV. Again, these are just different experts and different agencies making forecasts. As you can see, deterministic, point-based, and then on the right, model-based forecast, again, just assuming as a function of deployment. And what we did is that we collected, we wanted to see which of these two approaches, but when you're looking at the probabilistic approach version of these, was more accurate, and whether or not there were systematic differences going forward. So these are the research questions we asked in this particular project, which is what is the relative performance of these types of probabilistic methods when you actually compare them to 2019 costs. Again, this had not been done. And then are there any systematic differences between them that may give us a sense of what we should do going forward for designing these policies? And we again collected data for all of this. We generated forecasts using different types of methods. One was pioneered by Doyle Farmer and colleagues at Oxford using stochastic error approaches. Another one, we modified a method that was generated by Greg Nemeth at the University of Madison, Wisconsin. And then we also used these expert elicitations. And we did it for 6 technologies for which we could do a fair comparison. I'm happy to get into this. We basically took the forecast using models, using data up to the year when the experts had made their forecast. So kind of using the same date for making the forecast. Otherwise, it obviously would be unfair. And then we, for 10 technologies, we were able to do this to look at the differences to 2030. And the first thing, the first research question, I'll just quickly go through these results and the conclusion. We found that the model forecasts, which are the ones that are in the brighter colors, so the W1, which is for Wright's law, M1 for Moore's law, so the red, purple, blue, and green were the model-based forecast, and in black, we have the expert-based forecast. And what you can see from the beginning is that generally speaking, the model forecasts were more likely to include the actual value, which is on the vertical line, the discontinuous vertical line. So the uncertainty range, the 5th to 95th percentile included in most cases, in 6 out of 6 cases for the models, but in only 1 out of 6 cases for the experts. So in this particular case, the experts did worse. But then the other interesting that we found is that when you look at the median forecast, for all types of methods, again, like in many areas, nuclear is an exception here. Nuclear is very different. In nuclear, the experts were more optimistic than the models. What we see is that the median forecast using all methods was higher. So it underestimated the speed of technological innovation. Again, that's why I'm talking about a good surprise. So we have an underestimation of the pace of technological change. When we look at 2030, again, I'm not going to go through this in a huge amount of detail, but what you see is that on the right-hand side, in these gray columns, you have the expert methods. Usually the range is much smaller, so they're still overconfident. So experts don't, think they're more certain than what the world actually, the data that is available tell you. And then they're also more conservative. They're more pessimistic than these model-based methods. So again, if you use experts, you may end up being particularly pessimistic about the rates of progress, and that means that you will put in place more conservative policies also because the costs are higher. So what do we for nuclear, again, this is again, I could spend a long time on the nuclear piece. But so what did we learn from this? The cost of climate mitigation, at least in energy and at least over the past 10 years, are best estimated with model-based methods. They're quite uncertain. But all methods underestimated technological progress in almost all technologies. Most likely, and this is not something we can prove, but it seems reasonable, as I will show you later, that is likely as a result of structural changes that have happened in policies, in markets, in consumer behavior. So we have this underestimation that can lead to bad policy decisions or conservative policy decisions. So let me now jump and look at the benefits, other things. So I've looked at what is it that we know about the cost of these technologies and how this can inform policy making in different types of modeling frameworks of cost benefit analysis. Well, we've seen that renewables are not only coming down in cost, and of course, this is just renewables. In the other slide, I had other technologies. We also have things like electrolyzers for green hydrogen. Well, it's not just costs have come down. We actually do have a larger share of electricity from renewables around the world. But while there has been progress in electricity, fossil fuels still generate about 80% of total energy consumption, and it actually hasn't changed much over the past 10 years. But importantly, we do understand what is shaping both the cost and the deployment and the diffusion. Here we have the diffusion of these technologies. And this is a picture that gives you a very quick sense of how much activity there has been over the past. Well, here we have 10 years, but actually, when you look back, it's more 20 or 30 years. There have been a lot of energy policies around the world, mainly in power. So here, as we can see from a report by REN 21, 145 countries have power incentives, less of these in transport and heating and cooling. If you go back to 2004, there was hardly anything in heating and cooling and transport. There were around 30 countries instead of 145 in energy. And of course, we have now around 22% of emissions covered by some sort of carbon pricing. And then we also have net zero targets. So there's a lot of experience. And the good thing about this is that a lot of people, our group, but also many people around the world have studied and have looked at what do we know about the impact of these different policies on different outcomes. And again, the crucial thing that we were interested in this big review that we did, where we covered a wide range of papers, is what do we know about the impact of these policies, not just on deployment, but also on innovation, on competitiveness, and on distributional outcomes, right? Because we do know from that literature that I mentioned that it really matters, of course, and of course it's an ethical, I think, responsibility to really make sure that we don't leave most vulnerable communities, poor marginalized communities behind. So we looked at this. Again, it's hard to explain this without politics, but again, don't take my word for it. There's a huge amount of work on this, including my own. So we did a big systematic review to understand what is known about the impact of decarbonization policies, and we only covered 10. We're working on an expanded version of this systematic literature review. For those of you interested, we looked at various things. Basically, we looked at thousands of papers. We ended up with 211 papers and 705 evaluations that looked at the separate impact of specific policy instruments, and I'll show you which ones we looked at on different outcomes, on 7 outcomes. I'll just talk about 4 of them. So here, I'll take you through this quickly. This is one of the summaries that we have in this Nature Climate Change paper. where we look at the impacts of, it's actually 10 policies, but here you don't have, each circle is a policy. Here we don't have 10 circles for each of these indicators or outcomes, because for some of them there wasn't literature, right? So we have 10 policies. Just to give you a sense, RPS is renewable portfolio standards, R&D is R&D funding for clean tech, government procurement, this is green government procurement, FITs is feed-in tariffs, taxes and exemptions, GHG, greenhouse gas allowance trading schemes in cap and trade systems, auctions, renewable energy auctions, tradable green certificates, and then white certificates for efficiency in buildings. So we covered all of this. And the key message here, the numbers are the number of evaluations. What you can see is in blue, we have a positive impact. In gray, no detected impact. And in orange, you have some sort of negative impact. Generally, what we see for deployment indicators, do these policies get technologies on the ground? Generally speaking, yes. Or, or it's hard to measure with this particular paper, right? For when we have these auctions here, this is not, it's not that there were less, less renewable, it was less deployment of particular types of technologies. So there was a particular differentiation being made. In the right-hand side, other innovation indicators are some of these metrics that I discussed: cost reductions, patents, publications, eco-innovations, new products that were green. So we generally have a positive impact, no matter what method these studies use. Some of them use quasi-experimental econometric methods, which I use a lot in my work, but also others use things like surveys. But again, we have quite consistent impacts. It's very different when you look at competitiveness and distributional impacts. And here you see much more orange. What you see, competitiveness are things like exports, productivity, and cost of inputs and things like this. The distributional impacts are going to things like either small firms or vulnerable consumers or communities. So, and what you can see is that there's results are much more mixed. Some of these mixed results reflects the fact that the policies are a little bit different. So you can design auctions, renewable energy auctions, in a lot of different ways, or so some of it is policy design. And again, this is good because we can learn from this, and we discuss in this paper various ways to do this. One thing, for example, in the taxes is things like revenue recycling, which a lot of people have looked at. So we discuss this in more detail. I want to emphasize that this doesn't mean that overall these policies in these evaluations, these people, we didn't do this paper most of the time didn't do an overall welfare calculation. So this is just saying that some negative distributional impacts were identified on some people, right? So what this means is there are some short-term to medium-term impacts that if governments and policymakers are not proactive, you will have more and more of this as we put in place other policies. So again, this is not like a total calculation. These are just some people are worse off. Again, not super surprising, but we see it quite consistently. And again, for those of you who are interested in exploring this, we did this as part of a big European project, and we actually have, there are a lot of things that we coded in terms of the design of these policies, what was the magnitude of the effect, where these things happened, and you can, do your own filtering. This, it's very useful for both students and researchers and policymakers alike. Here is the link. But the key thing I wanted to mention, which might not surprise many of you, is that when we actually plotted where did we have this information about the impacts of different policies, you see, again, not surprisingly, it's mostly OECD countries, right? We have OECD countries, and we have, some China, India, and Brazil. So there's a lot that we don't know, and we're working a lot on trying to develop the evidence base, the original research for developing countries, especially Sub-Saharan Africa. So this is very much ongoing, and we're seeing some big differences in terms of the impact. Just the UK, just to give you a sense, there were 48 papers, so compared to nothing for many other countries. And the important thing, beyond the fact that we have a lot of evidence now that these policies, have an impact on innovation and deployment, but have some mixed impacts on other outcomes, when we think about the models that are being used to support policymaking around the world, in the US, in the European Commission, in different countries, we see that models are not incorporating all these different ways in which policies affect innovation and competitiveness. So again, they're underestimating not just, they're overestimating the cost, but they're also underestimating the benefits, in that they don't show that you do have, in some cases, impacts on competitiveness. You have other, spillover effects. So all these mechanisms that we found on the innovation indicators, most of the models are not including, none of them are including all of them. We did this as part of a big UK-based funded project with colleagues at UCL, at Oxford, and around the world. And no model was looking at all of these channels for innovation. It is difficult, but they're not all including it. They're not including other products. And many, some do, but many don't include this endogenous technological change, how actually policies shape this. And many models don't include all these different policies. So they may include a carbon price, but they don't include other policies. So again, we do need a new set of tools and more complexity to do this. So we may be underestimating the benefits that come through spillovers, through new products, through industry competitiveness. So let me now focus on one aspect of this, on this impact. And this is, I've done quite a lot of work in this space, and actually is one of the areas in which I think there's a lot of growing strong evidence that we can, again, with well-designed policy, have both things, advance innovation in low carbon technologies, but also improve opportunities to displace workers and to to address also some of the economic goals that most governments have. And this is looking at the impact of specific public support for energy on startups and small firms, which again make up the majority of firms in most countries around the world, and jobs, of course. So there's broad consensus, as I kind of hinted at the beginning, that is necessary to increase public funding for energy R&D. Right now we're around 30 billion a year globally, up from 25 in 2015. And there's an increased interest in how to manage and allocate funding. You may know, this is more niche, but there are both the European Union and the UK government and also countries around the world are considering new institutional mechanisms for disbursing either increased R&D or for making the R&D that they're making more effective. And again, there's a growing interest in the role of new players, startups, so small companies. And there's a whole literature on this, on the disruptive innovation and things like this. And there is, a lot of, I've done quite a lot of work on this with colleagues on the US. That's where we've been able to get a lot of data. There's a very big energy innovation ecosystem. So actually this idea that in the energy sector, in innovation in the US, is just the market doing its thing. There's a huge amount of activity and a huge amount of institutions that have been put in place by the US government. I'm not going to go through this. This little graph shows the many institutions, and I'll talk about a couple of the things where we've done a lot of detailed empirical work at the firm level. ARPA-E was a new agency that was created in the last crisis, in the 2009 crisis, modeled after DARPA to fund research both in firms and also in universities. And we've looked at the impact of this. We have done a lot of work looking at the role that national laboratories, which are huge. There are 17 of them in the energy space in the US, with around 14 billion a year in funding. So there's this big infrastructure. The UK doesn't have it because they were privatized in the 1980s. And we've looked a little bit at what is it, have they been helpful? Have they played a role in supporting clean tech startup innovation in the US? To help, and the other piece of evidence to see that this is relevant for other parts of the world is that while in the US about 12% of our R&D is conducted by things like public research institutions like national labs, in over 68 countries, 30% of research is done in things like national laboratories, so publicly owned institutions. So we've looked at this, and I will quickly go through this. The first thing is looking at these national labs, and this was something that really surprised me. We looked at all of the partnerships that US clean tech startups had in the US with things like national labs, with universities, and with other firms. My ongoing assumption was, those that partner with other firms, they're going to get these market relationships, they're going to learn about customers, business models, and they're going to do better. To our surprise, we did instrumental variables, different types of matching, a lot of different things. We found that at the firm level, the ones that were doing better in patenting and business growth were those that had partnered with national labs, which again, we do a lot of network analysis, using various metrics. Again, you can go to the research policy paper. We then found, that we could explain this in a range of ways, looking at the fact that these national labs are major, they have expertise and networks, a critical mass of employees, complementary technologies. They also didn't have, this incentive to compete or steal information. Well, steal, I'm using a strong word, but I think you get what I'm trying to say. They also have infrastructure, hardware. They have around 200 facilities. And then they also provide, they also have inventions for licensing. And they also, investors take engagement with national labs, which of course have a big reputation scientifically as an extra quality check. So it was easier to secure funding. So they were very important for these startups. And then moving on to the other entity, which again is an area where the European Union is trying to create an ARPA-like funding agency. The UK has been thinking about doing this through something called ARIA. So the idea is that, trying to understand whether the DARPA model has also been successful in the energy space. And when we look at the first cohort, and again, this is a limited study, we just look at one cohort of startup awardees, we found that actually they were doing much better in terms of patent. Also, when you do something similar to a regression discontinuity design econometrics approach, where you compare them to rejected applicants, which are not just bad, are those that just made it, right? So these had already gone through several levels of analysis. So again, we have enhanced post-RPI patenting, even controlling for all kinds of things. Interestingly, again, this entity, as you could see in the previous graph, there are a lot of different institutions. It's not designed to fill on the gaps. But what we saw is that while on post-award business success, those recipients of RPI funding that were startups performed better than rejected applicants, they weren't doing much better than others who hadn't applied. That is partly because there are technologies in the market that were less risky. But we also found that, of course, you do need this demand pool that I was talking about, and some of these technologies are in market where you don't have a lot of these demand pool policies that are buying down the cost. So there's a lot of more work on this, but generally we found actually that RPI had been very effective on a lot of the different metrics. And again, this is something that aligns with some other research that has been done along the way on public support, especially for small firms. Sabrina Howell also finding similar things for one of the different other US Department of Energy entities funding small firms. And Jacqueline Pless, who is at NYU and has also done similar work, actually looking at the UK and looking at this. But again, a key conclusion is that additional support mechanisms are also needed to bite these technologies down. So you need both the technology push and the market pull. And then the final point I'll make before I get to the conclusions, I think I have about 5 minutes, is, we've looked at the costs a little bit. We looked at the benefits, some of the new research, what you need to look at, where you need to be proactive, otherwise you get to these negative distributional impacts, is what are the things that make it more likely that if you are a country and you're putting in place some of these policies to address the climate challenge, but also to create new opportunities for and sustain or economic growth, you need to think about what are the mediating factors that are going to mean, well, you're maybe going to develop some comparative advantage in a particular industry or part of an industry. And this is where we talk about the role of technology. So not all technologies are equal. A nuclear plant is not the same as a refrigerator. Again, it's something really important, as you will see. And even within the same industry, different components which have different levels of value add. And here in wind, we have a lot of different components. Some are very basic, less complex, less kind of profit for it. And some are more complicated, like things like generators and blades. So there's been, again, quite a lot of developments over the past here, maybe I would say even, 8 years, 7 years or so, looking at what are the factors that can shape the extent to which different countries may be able to develop domestic, manufacturing capabilities or, comparative advantage on things. And there are a couple of concepts that have emerged that we can measure. Some are related to technology complexity and industry structure. So here, looking at things like analyzing using machine learning and text-based analysis patterns, as well as exports. Again, exports is something where we can look at relationships, and we can map complexity of exports using the product complexity index, which was pioneered by Cesar Hidalgo in 2007, and it's been adapted, including by our group, in various things. So higher complexity of wind, in which I will show you, a visual representation of this, has meant that you have less countries that have been able to manufacture, even after a lot of policies, some of the more complex components. So again, when you're thinking out what might be some of these benefits, you should also be realistic about what you might be able to achieve. Some of it depends on technology complexity, and some of it on your own domestic capabilities, right? These are some of these economic geography concepts on technology relatedness. So this is quite important. There's a lot of work on this. Another one is looking at design and manufacturing complexity. And then things like other factors about standardization, right? So when you have standards, you may be able to more easily perhaps access export markets. we have a global innovation system, which means that often, as I will show you, components are made in different places. And I will conclude, there's, well, two quick things on this point, just to illustrate where the research is on this area. Here, this is a study that we published last year in Nature Energy, and we managed to get data for over 10 years on all the different firms along the global value chain on wind. So not just the overall equipment manufacturers like GE, for example, but also the manufacturers, the smaller firms, again, with the theme of small firms, looking at components. There are 9 of them. Here we have from left to right. This shows increased complexity. So towers are the less complex thing to do. It's basically concrete and things like that. And on the right, you have things like gearboxes. On the top row, we have the status of exporters and manufacturers as of 2006. In the bottom, 2016. And the key thing I want to show you here is that while there was a growth in the number of countries that were engaged in towers, so you have a lot of little lines at the bottom for towers on the left and very few on the top, that kind of diversification, emergence of manufacturers that we saw in towers across 10 years didn't happen in gearboxes, not nearly to the same extent. So again, showing that, and it's the same when you look at things beyond experts, if you look at other metrics for complexity. So again, results hold for pattern-based complexity metrics using machine learning. And again, why is this important? Well, you do have a lot of countries that are trying to do this. They're trying to put in place policies to develop domestic industries. One example of another paper we did also in Nature Energy was looking at local content requirements for solar auctions in India, and we found that cost came down a huge amount, but we found that there were these local content requirements because, of course, you're limiting what components you can buy, did lead to an increase in the cost of electricity during the period when it was implemented. It was just a policy that wasn't looking at this push and pull. So this doesn't mean that if you implement it differently, you cannot reduce this cost increase and also lead to more domestic manufacturing. But we saw that there was not, while there was short-term increases in manufacturing, there was very little impact in export markets. So some of these other competitiveness goals weren't quite, again, there are many reasons for this that we discussed in the paper. So this is, again, countries are juggling with this. So let me now conclude with the key messages. The first thing, just going back to my first slide, we need to build a more inclusive, sustainable, and resilient society. We need, a more systemic, purposeful policy effort that represents a step change. Again, those graphs make it clear. But we also have a lot of things that are, we can do, which is to leverage all this accumulated experience that I've been describing. This means that a strategic investment, both in R&D, deployment, demonstration, early markets, and regulation, again, well-designed with the most vulnerable at the center, can help build both support for these policies and also advance multiple societal goals. The other thing is that decision makers also need to consider, especially if they're also looking at these other goals, differences across technologies and domestic capabilities to address the full innovation system. And finally, and I think this is very important, this is one of the most exciting areas for me, and I don't know if for all of you, since you'll go into the labor force, I think there really is an opportunity to change how things are done. I mean, a lot of other people have been mentioning this, Mariana Mazzucato, for example, but what we are seeing through this analysis is that the current policy support tools and processes are biased in overestimating cost and often underestimating at least some of the opportunities. Cost-benefit analysis is not always suitable for things big like this. We need big changes across a lot of things that are better for marginal improvements, but not so much for this. So we need new capabilities, new processes, and ultimately new institutions in policy making around the world that account for this. And finally, thanks to all of you for listening, for your attention, and to all my wonderful co-authors for making this fun.
Thank you very much, Professor Diaz. I think we have exactly 15 minutes for the questions, and we have a bunch of questions.
Shall I remove the screen, or what do you want me to do, Arif?
Sure, yeah. This way, the audience can see you directly. Mm-hmm. So I would like to start with Alex's question. Alex, do you want to unmute yourself and ask for yourself?
Sure, I can do that. So I asked 2 different questions in the chat. The first one was, going back towards the beginning, I wanted to know how realistic you think the net zero for the 130 countries is between 2050 and 2070. Particularly, does a lot more need to be done in the area of research and development, or are we on track to hit those goals?
Yes, so thanks for the question. It's not, we're not on track to meet those goals right now. That's why one of the things that was emphasized during the COP is that while the Paris process worked in the sense that yes, 6 years after Paris, initially it was going to be 5 years after Paris, now it was 6 years after Paris. Most countries revised, and many of them made their nationally determined contributions, their NECs, more ambitious. We're still not on track to get to net zero by, let's say, 2050. So some of the analysis that have been made by entities like Carbon Tracker, by the UNFCCC, which again I mentioned at the very beginning, suggests that if with the NDCs that have been, the NDCs are around now 2.4, again, assuming they're implemented and do what the countries think that they're going to do, again, and those are big ifs. So with the additional pledges that were made in the COP that go beyond the NDC, so some of these other pledges that were made around methane, around deforestation, those are not included in most of the NDCs, then maybe we are more on the 1.8, 1.9. But again, this is assuming that they work. So, with the things that have been put on the table, both more formally through the NDCs or outside the NDCs, we're not on track with this. We do need more, R&D demonstration and scale up, regardless, but we also need to get a faster diffusion of some of the technologies that we already have at a mass scale. Again, I showed some of the, what we're seeing already for renewable energy deployment. The numbers are quite impressive also now, especially the last couple of years for electric vehicles due to these big cost reductions in lithium-ion batteries and also incentives. But yeah, we're not on track now.
Thank you. So the other question I had went back to the CO2 equation that you had that had particularly the term of energy, the energy part of that equation. Is there sort of a difference when making that CO2 calculation between like clean energy that comes from maybe like wind or solar power versus like dirty energy that comes from oil and coal?
So that is represented in the last term on that equation. So that is basically this chi identity. It was simultaneously proposed by people like John Holden and Paul Ehrlich, the IPAD equation, impact equals population, affluence, and technology, and Kaya in Japan. And basically what you're referring to is the last term of the equation, which is carbon intensity of energy. So that is, what is the carbon emissions? These are in a lot of the big kind of equilibrium models and life cycle analysis models, this would be the carbon intensity of energy generation. So CO2 emissions per joule or per kilowatt hour. So that's where you would have, that number is quite high, very high for coal, but much lower for wind. So that's where most people who think about innovation, they think, oh, this will affect the carbon intensity term, but in fact, it also affects the other two.
All right, awesome. Thank you so much.
Welcome, thanks.
Someone from the audience asked, what is your view on policy adoption on nuclear tech going forward?
Policy adoption on nuclear what?
Technology.
On nuclear technology. Well, so this is, an area I did some detailed work on this in environmental science and technology back in 2013. And we were covering mainly, the EU and the US. So we did some, work on these expert elicitations. We did Delphi method. We had experts from both the private sector, national labs, and universities. And we were basically trying to understand the cost, what the cost might be going forward, and when next generation reactors might come up, and whether small modular reactors might be cheaper than the utility scale 1 to 2 gigawatt reactors. What we found back in the day, and I'll get back to the present in a second, is that by 2030, by 2035, most experts thought, and just looking at the data that we have seen, some of which we have in this subsequent study in PNAS, is that at least in these big markets, costs have gone up, not down. And they didn't expect that to 2030, this was back in 2013, cost, might, in these geographies are going to be, continue to be expensive. Now, there are a couple of things to say now going back to the present. As far as we know, in these geographies, the costs are still not competitive with a lot of other technologies. Having said that, okay, so right now things are very different. They have less kind of certainty about their costs from places like China, but there what I hear and is that costs are much cheaper. I'm not sure if it's quite competitive with some of the other technologies on a per kilowatt hour basis. Of course, the difference is that nuclear is a base load firm power, and this is one of the areas where, as we go past right now, where on average in the world is 29% renewables. Only some of that is intermittent, but in the UK it's around 42% renewables. As we get further into renewables, we'll need more. The baseload power, firm power is more important. There are other technologies that could work here. There's some other storage technologies, other types of batteries. There's things like geothermal. There's things like green hydrogen. So from renewables, electrolysis, and hydrogen, which you can store. So it is one of the. We will need, to keep exploring different opportunities. Right now, it's expensive. If a lot more is built, maybe things can come down. But again, it's very it's very much something that I find it hard to say one should cut it off completely, especially in the research and in some of these new designs. But I think because they're so lumpy and the cost is so high, it's a very hard balance. So in many countries, the decision has been made to not do nuclear and maybe go into other areas. I think having some of the research capabilities, some of the demonstrations for some other technologies may be wise from if you are a big country, obviously this is very much dependent on, on critical size. So there are a lot of things there related to the time, the cost, the size, the capability, but it could play in some places, depending on how other things evolve. It's something that, keeping alive, I think, will be important.
Okay, someone from the room asked, you have mentioned that competitiveness co-benefits decarbonization. However, you have also mentioned the role of patents in the process of technological innovation. So do you think the technology sector needs re-regulation to achieve competitiveness and hence greener technology innovations?
So is the question whether we should get rid of patents? Is that, maybe I can...
That's what I understand.
Okay, yeah, sorry. Well, so there's a huge amount of research on this topic. I haven't done research myself on, on the dual impacts on patents, both on, incentivizing innovators to innovate and therefore resulting in more innovation, new technologies, new breakthroughs. But of course, it also has it protects technologies, so it reduces competition because it doesn't allow other actors to get engaged. And I think where the literature, again, I'm not an expert on this, but I have, I use patents in a lot of research as indicators of innovation, again, with a lot of the caveats that come with the use of patents. And what we do see in some of the literature is that it depends also on the sector and how patents are used in the sector. So, when we think about things like, in some sectors, they're not very used. In some others, they're used proactively. There's, patent, trolls and, hoarding and things like this. So I think this is, I would say two things. One, there's some evidence that it depends by sector. And second, there's some evidence that in some cases, patents have been more of a detriment. But also in other areas, you see that, it's hard to explain some of the good things that happen without them. So I don't think we have, there may be some argument for differentiation of patent regimes. I'm not sure it's going to happen. It's very difficult. But yeah, I do think there's some evidence that in some areas, and of course now we're seeing some of the discussions with COVID vaccines and things like this, where it's not an issue in things like solar PV because now it's a commoditized technology, but for some of the other technologies there, or wind even, with some exceptions. But for some of the other technologies that are coming, maybe it's unclear. There may be some scope for doing reforming patents, but again, it's not my main area.
So what is the kind of research and development efforts required to develop effective decarbonization technologies, and how can this be financed? How can this be financed, especially in developing countries, and to what extent could this goal compromise other goals of alleviating poverty?
Yeah, no, thank you for the question also. So that I think it's very important to, a lot of the research that we have on these topics, including the one I do, I've done some research in China and India, but again, there's more data, they're big. It is looking at the experience of industrialized countries or some of these big emerging economies. The thing to say about research and development is that it's cheaper compared to other policies, right? When we think about what is the cost of doing things like, feed-in tariffs or, demanding putting heat pumps or things like this, is relatively cheap. Having said that, okay, the evidence that we have is that some R&D and some capability, even in the small developing countries, is useful because you need some people from, who understand the local context to be able to even adapt or, make decisions about what to deploy, right? So what to, pay for, what to do. So there's some value in having domestic capabilities, which, to some extent, you need to have some R&D on. But the extent to which R&D would be justified on the basis that then, those countries would become global exporters or competitive in areas. Again, what I was trying to show kind of towards the end is that it really depends on the technology. So I think it's a balance. That's why I'm really trying to look at this balance between, especially for developing countries. And again, we have a lot of ongoing work on this too, that, some might be needed for just being able to do things. Some of it might be needed to develop technologies. But you cannot always count on, R&D, sometimes takes quite a bit. It can take, some of these technologies that we've been talking about, they were spurred by public R&D efforts in the oil crisis in the 70s and 80s, right? So there's also this question of timescale and other goals. But again, the one good thing about things like R&D and demonstration is that it's generally cheaper than other things. But yes, there is a calculation in which the possible payoffs for the countries really depend on the size, on the other, industry that the country has, etc.
The final question is again from the room. Do you think the current global banking finance system can adapt to accommodate the current need for funding in R&D in net zero technologies? Or do you envision this as something coming mostly through the government, similar to ARPA program?
ARPI? Oh, ARPI, yes. So for the R&D, there's a lot of work on this, and what we see is that in the when we think about the post-war efforts in the 40s, 50s, even 60s, especially in the US, but also in other parts, there were really large kind of vertically integrated companies that were, because of the incentive, they were essentially monopolies. They were doing a lot of the basic kind of research. It's an arbitrary demonstration. I would rather call it research and development. As and what we see is that a lot of those broke down. The industry changed. There are some questions about whether companies like Google or Amazon are doing some of the same sort of thing. I think kind of they're different sectors. And again, if they're doing it, maybe they're not doing as much, publishing and things like this. So I think it's the role, and this is something that we know overall in research, not just in energy. When we get closer to commercialization, and indeed we're in commercialization, the role of the private sector, the fraction, let's say, of the efforts becomes greater. So I think for a lot of these technologies that are the early stages of development, that have in the technical speak the lower technology readiness levels, again, traditionally and even more so now, the role of governments is essential. Again, and also the role of governments, not just do funding, ivory tower kind of people in academia, but also funding some of these interface with firms, because we saw that from this research that without this research funding that goes to some of these entities, they wouldn't be doing as well. So it's an important, it's a hugely important role. And again, there's a huge literature on this, knowledge spillovers, externalities, and so forth. So I think, yes, they've pledged also as part of things like the Paris Agreement and Glasgow to complement mission innovation and public R&D funding, but they will not replace it.
Perfect. Thank you very much for coming to speak with us, Professor.
Thank you for the invitation.
It was very interesting to learn about some of economics concepts, and also how do they impact the technological innovations and the policy about technological innovations. Thank you very much for everything.
Thanks, Sue. Bye. Have a good conference.
Thank you. And for the audience, our next panel will start in 15 minutes, so feel free to stay on Zoom. Hi, Pia.
Hi,
Hi, how are you?
I'm good. How are you?
I'm fine as well. I'm sorry.
I was wondering what was happening here because I joined this Zoom and everything was like completely quiet and it said recording, so I didn't want to like start talking in case there was like some sort of live stream or I don't know.
I'm so sorry. The last speech took a bit longer than usual.